Jimmy Akin's Mysterious World is brought to you by the Star Quest Production Network and is made possible by our many generous patrons. If you'd like to support the podcast, please visit sqpn.com/give.
Previously on Jimmy Akin's Mysterious World.
Throughout human history, people have wondered about the world around us. How did it begin? How was it structured? Are we living on a flat Earth? Are we living on a ball? Are we at the center of the universe? What are the planets? How far away are the stars? Well, we'll be talking about all these questions and more on this episode of Jimmy Akin's Mysterious World. And here was the kicker. In the letter, Hubble used the exact same technique for gauging a distance to the spiral that Shapley had devised for mapping the arrangement of globular clusters around the Milky Way. Applying the Cepheid period luminosity formula that Shapley had derived, Hubble calculated a distance to Andromeda of around 1 million light-years.
In other words, Hubble politely threw Shapley's own Cepheid formula back in his face and showed that Andromeda really was 1 million light-years away, which meant, in turn, that it was another island universe. And that is how we found the universe. We now knew that the Milky Way is just one in a sea of island universes.
You're listening to episode 245 of Jimmy Akin's Mysterious World, where we look at mysteries from the twin perspectives of faith and reason. In this episode, we're talking about how the universe began. I'm Dom Bettinelli, and joining me today is Jimmy Akin. Hey, Jimmy.
Howdy, Dom.
Many ancient cultures held that the world has always existed. Greek philosophers like Aristotle taught this, and they helped give the idea intellectual prestige. But the Bible teaches that the universe began a finite amount of time ago when God created it in the beginning. When Europe was thoroughly Christian, this view was accepted. But with the scientific revolution, many thinkers reverted to the view that the universe was static and unchanging, that it had always existed. Then, in the 20th century, startling scientific evidence emerged that the universe did have a beginning. Information emerged that suggested the universe began around 13.8 billion years ago in a fiery event now called the Big Bang. What is the Big Bang? What evidence points towards it? And what are its implications? That's what we'll be talking about on this episode of Jimmy Akin's Mysterious World. Jimmy, this episode is a sequel to episode 206 on how we found the universe. To set the stage, tell us about that episode and how this one will be different.
In episode 206, we told the story of how we determined the overall structure of the universe. Originally, we didn't know about stars and galaxies. We knew the stars existed, but we didn't know what they were. Going back to the time of the Greeks, people thought the universe was a set of concentric shells with Earth at the center and the sun, our sister planet the moon, and the other planets orbiting on crystal spheres that surrounded the Earth, nested inside each other like a Russian matryoshka doll, and the outer shell of fixed stars beyond those. But eventually, people recognized that the stars are at different distances, so there isn't a single outer shell that they're part of. They also realized that the sun, moon, and planets aren't attached to shells either. And after Isaac Newton introduced his theory of gravity in the 1600s, a picture of the universe emerged and became accepted where the Earth and the planets orbit the sun, which is one of the stars in a vast sea of stars. People also started thinking about that vast sea of stars, and they realized that it's shaped like a disk. They thought that the disk of stars was the only thing that existed in the universe, and so they called it the universe. The image of the universe was now just a disk of stars floating in a vast, dark sea of nothingness. Except there were these little fuzzy patches of light in the sky known as nebulas, and some of them were spiral in shape. Into the 20th century, there was a debate about the spiral nebulas. Were they objects here in the universe, the disk of stars, with us? Or were they far outside the universe? Were they island universes of their own? In the first half of the 20th century, that question got answered. the spiral nebulas were island universes of their own, or what we now call galaxies. And suddenly, the dark, empty cosmos was filled up with a web of galaxies. But one thing that many astronomers were still assuming about the universe was that it was infinite in space and time. It stretched on forever and ever in space, and it stretched back forever and ever in time. It had always existed. Today's episode is the story of how that view changed, how we came to realize that the universe, at least as we experience it, had a beginning.
In the introduction, we said that many ancient cultures have held that the world has always existed. Don't all cultures have creation stories?
Cultures tend to have what we, in a Judeo-Christian context, would call creation stories, but they usually don't mean what we do. We think of God creating the world out of nothing, or creation ex nihilo, to use the Latin phrase. However, most cultures aren't thinking about creation out of nothing. Instead, they think that the world was made out of something that existed eternally back into the past, or at least something that didn't have an origin so far as they knew.
Can you give an example of that?
Sure. To cite a famous example, in his dialogue, the Timaeus, the Greek philosopher Plato said that the universe was built by a supremely powerful being known as the demiurge. The original Greek term demiurgos means artisan or craftsman, and like an ordinary craftsman, Plato's demiurge needed to work on something to practice his craft on. Only since materials like wood and metal didn't exist yet, Plato's demiurge contented himself with working on chaos, which was the only thing visible that existed at the time. The demiurge used the chaos to make triangles, and he put the triangles together to make geometric solids and produce the elements air, fire, earth, water, and ether. And from those, other things got made, letting human craftsmen work with things like wood and metal. For our purposes, though, the important thing is that the demiurge didn't come up with the original chaos from nothing. As far as the Greeks knew, the chaos didn't have an origin. It had been eternal. Other cultures had similar ideas. In Egypt, there was originally a lifeless, primordial, watery chaos. Then a pyramid-shaped hill known as the Benben came up out of the sea. One of the gods appeared on the Benben, and then he made the other gods. But the primordial ocean was there in the beginning. In the Mesopotamian creation story, known as the Enuma Elish, there were originally two primordial water deities, Apsu, who represented sweet water, and Tiamat, who represented salty, bitter water, and they commingled, and then the world was ultimately formed from them. So this is a common picture of how things came to be. It's not a story of creation out of nothing, but of creation out of something. And that was pretty standard in ancient worldviews. You find it in lots of cultures.
If the idea of an eternally existing universe was common in ancient cultures and among astronomers, how did we come to realize that our universe has a beginning in time?
The first step on this journey is found basically where episode 206 left off. You'll recall that in the 1920s, there was an astronomical event known as the Great Debate about the structure of the universe. Harlow Shapley defended the idea that the Milky Way is enormously huge, and that the spiral nebulas, like the Andromeda Nebula, were inside of it, while Heber Curtis argued that the Milky Way was small and the spiral nebulas were far-off island universes outside the Milky Way. The debate ended pretty inconclusively and didn't really settle the question. Curtis had some good arguments for the spiral nebulas being outside the Milky Way, but there was also a really good counter-argument at the time. One of Shapley's colleagues, Adrian von Manen, had been taking measurements of stars in the spiral nebulas, and it looked to him and to some other astronomers like the nebulas were slowly rotating. That was a problem for the idea that they were huge, far-off island universes, because if we could see them rotating, it would mean that the stars on their outskirts would be traveling faster than the speed of light, which Albert Einstein's new theory of relativity said couldn't happen. So many astronomers thought that the spiral nebulas must be close by. They must be smaller objects that are here in the Milky Way if we can see them rotating. It later turned out that the apparent rotation was just an optical illusion, but they didn't know that at the time, and so the issue remained unsettled.
What finally settled the matter?
A measurement taken by Edwin Hubble in 1924. He found a star in the Andromeda Nebula that he could measure the distance to, and it suggested that the Andromeda Nebula, now called the Andromeda Galaxy, was 1 million light years away, far outside the Milky Way. Later, it was discovered that the Andromeda Galaxy is around 2.5 million light years away, so even further. Hubble even used a technique that Shapley himself had used for measuring stellar distances, and so Shapley had to conclude that Hubble was right. Hubble sent him a letter announcing the finding, and as Marcia Bartusiak writes in her book, The Day We Found the Universe,
Shapley, upon reading the letter, immediately grasped that Hubble's finding spelled doom for his cherished vision of the cosmos. Harvard astronomer Cecilia Payne happened to be in Shapley's Harvard office when Hubble's message arrived. He laid out the 2 pages to her and exclaimed, "Here is the letter that has destroyed my universe."
So even though the great debate was long over, the issue was finally settled, and we now knew that we are living in a universe filled with galaxies.
When did the idea start to emerge that the universe had a beginning?
The groundwork for this had already been laid, some of it way back in time. Back in 1666, Sir Isaac Newton had demonstrated that white light is a combination of different colors of light. He did this by using a prism to separate white light into the colors of the rainbow. In fact, it was Newton who coined the term spectrum for the light that you could make appear out of white light. In Latin, the word spectrum means specter or apparition. I'm not sure if he used this word because he thought the colors he was making were ghostly or just because he made them appear, making the word apparition appropriate, but the name stuck. Later people also experimented with separating light into spectrums, and they noticed something strange. The spectrum of colors would have these little bright or dark lines on it. It wasn't a smooth rainbow. Sometimes there would be unexpected dark lines on the rainbow or unexpected bright lines, and since these lines appeared on a spectrum of light, they came to be known as spectral lines, and people didn't know what caused them at first.
Eventually, they figured out that these lines were caused by light interacting with matter. How does that work?
If a ray of light passes through an atom of element 1, or hydrogen, some of the light would be absorbed by the hydrogen, and it would be that missing light, which the hydrogen had absorbed, that was responsible for the little dark lines on the spectrum. These dark lines thus became known as absorption lines, because it was the light that had been absorbed that caused them. On the other hand, if you had some matter that was glowing and emitting light, it would emit certain types of light, and that was responsible for the unexpected bright lines on the spectrum. So they became known as emission lines because of the light being emitted by the glowing matter. What people realized was that between the absorption lines and the emission lines, you could tell what kind of matter the light had passed through or what kind of matter was generating the light, and the field known as spectroscopy was born.
What kind of new things did they learn using spectroscopy?
One of the things it helped do was settle a question that a lot of scientists, or natural philosophers as they were then called, never thought we'd get an answer to, namely, what are the stars made of? The sun was impossibly far away, and the stars were even farther than that. Nobody had a way to reach them and take samples of them. So what they were made of was thought to be an unsolvable riddle, just something we'd have to wonder about forever with no way to prove it one way or the other. But with the birth of spectroscopy, you could spread out the light coming from the sun or a star and into a spectrum and then see what the spectral lines on it were. That would tell you what the sun or the star was made of. One of the things that they found when they did this to the sun was that it, like most stars, has a lot of element 1, or hydrogen, in it. Our sun is 92% hydrogen, and most stars are about 74% hydrogen. So now we knew that the principal component of the stars was hydrogen.
But there was another surprise, because in 1868, the English astronomer Norman Lockyer discovered something else. What happened?
He noticed a bright yellow line where there shouldn't be one. Lockyer realized that this bright yellow line was an emission line being caused by an unknown element. And so he, like a few later natural philosophers, had used spectroscopy to discover a new element. The Greek word for the sun is helios, and so he called the new element helium, which we now know is element 2, the next one after hydrogen. It's about 8% of the sun, which is to say that it's almost all of the sun after hydrogen. The remaining elements in the sun are only like 0.1% of its mass. Most stars also have helium. About 24% of most stars would be helium. And the remainder of their mass, when you take out the hydrogen, is only about 2% of other elements.
Now that spectroscopy had solved the mystery of what the stars are made out of, there was another mystery that presented itself. What was that?
To understand this one, we need to mention an Austrian natural philosopher named Christian Doppler. He was born in 1803 and he died in 1853, and he's famous for a principle that's named after him, the Doppler effect. The Doppler effect involves an object that emits waves, and these can be any kind of waves. They can be physical waves, like waves of water on a pond, or sound waves moving through the air, or light waves moving through space. The key thing is that if the thing emitting the waves is moving towards you, then the waves bunch up together, since after one wave is emitted, the object has moved closer by the time it emits the next wave. And the result is that the waves emitted by the source moving towards you appear to have a higher frequency. By contrast, if the source of the waves is moving away from you, then the waves get spread out. After one wave is emitted, the object becomes more distant by the time it emits the next wave, and the result is that the waves emitted by the source moving away from you appear to have a lower frequency. This is why the sound of a train whistle or a car horn changes as it passes by you. As it comes towards you, the sound waves bunch up, so the noise becomes higher in pitch, and after it passes you, the sound waves get stretched out, so the noise becomes lower in pitch.
Why is that important for our purposes?
As we said, it doesn't matter what type of waves these are. They can be waves of water, waves of sound, waves of light, or anything else. Now, galaxies emit light, so if a galaxy is moving towards you, the Doppler effect will cause those light waves to bunch up and appear to have a higher frequency. The blue end of the color spectrum has the higher frequencies of light, and so if a galaxy is moving towards you, its color will look more bluish, and we say that the galaxy is blue shifted since the light is shifted towards the blue end of the spectrum. While if a galaxy is moving away from you, the Doppler effect will cause the light waves to stretch out and appear to have a lower frequency. The red end of the spectrum has lower frequencies of light, so if the galaxy is moving away from you, its color will look more reddish, and we say that the galaxy is red shifted because the light is shifted towards the red end of the spectrum. But it isn't just the light that the galaxy emits as a whole that is affected. It's also the spectral lines that you can see on the spectrum of its light when you spread it out. For example, element 20, or calcium, has certain characteristic spectral lines. If a galaxy is moving towards you, those lines will be pushed over towards the blue end of the spectrum, while if the galaxy is moving away from you, the calcium lines will be pushed towards the red end of the spectrum. And by measuring how far those spectral lines are shifted, you could get an exact mathematical measurement of how red-shifted or blue-shifted the light from the galaxy was.
Who was the first person to make blue shift, red shift measurements like that?
His name was Vesto Slipher, and he worked at the Lowell Observatory in Flagstaff, Arizona. We talked about the Lowell Observatory in episode 179 on Life on Mars. It was founded by the philanthropist and polymath Percival Lowell, who was convinced that there was a civilization on Mars. Vesto Slipher was an astronomer at the observatory, and he supervised the work that later led to the discovery of the planet, it is a planet, Pluto in 1930. But much earlier than that, he had made important discoveries on his own. In 1912, he was the first person to observe the shifting of spectral lines in light coming from spiral nebulas, and this was a dozen years before we even knew that the spiral nebulas are distant galaxies. He found something that was really surprising. He measured the light from 25 spiral nebulas, and 22 of them were red-shifted. Only 3 of the nebulas were blue-shifted, so that was quite strange. If the red shifts were really indications that the galaxies were moving away from us, and that was a question that was unsettled at the time, it meant that they were moving away from us really fast, and the farther away they were, the faster they seemed to be going. But Slipher couldn't do much more work on the problem because of the size of the telescope he was working with at the Lowell Observatory. It wasn't big enough to gather enough light to get measurements from more distant galaxies. So Edwin Hubble, who had a bigger telescope at the Mount Wilson Observatory in California, started looking at the problem. After he measured the distance to the Andromeda Galaxy, Hubble turned his attention to looking at galactic redshifts. Marcia Bartusiak explains,
While it appeared that Hubble had clinched the astronomy's brass ring, solving the mystery of the spiral nebula once and for all, a nagging problem remained: how to explain the galaxy's astounding velocities, first spotted by Vesto Slipher in the 1910s. Why were the spiraling disks speeding away from us? "They shun us like a plague," exclaimed British astronomer Arthur Eddington. It was a puzzle whose solution would prove to be even more momentous than Hubble's settling the island universe controversy. Hubble began to focus his full attention on the cosmic exodus in 1928. Having conquered the mystery of the spiral nebulae, he was now commencing his next great challenge, to see if there truly was a definitive trend to the redshifts of the galaxies as they rushed headlong into distant space.
and he had a lot of success in this.
By 1929, Hubble had determined the distances to 24 galaxies, including the small and large Magellanic Clouds, the most remote then judged to reside some 6 million light-years away. He accomplished this feat by establishing a ladder of measurements, one rung leading to the next. First, he used Cepheid variable stars, his most reliable yardstick, to directly obtain the distances to 6 relatively nearby galaxies. Then he judged the magnitude of the brightest stars in those galaxies. Figuring such stars were similarly bright in other more distant galaxies, he proceeded to use them as standard candles. He sought out these radiant stars in more far-off galaxies, 14 in all, and estimated each galaxy's distance based on the star's apparent luminosities. Then, taking all 20 of these galaxies into account, the first 6 and the subsequent 14, he estimated the brightness for an average galaxy and used that value for judging the distance to 4 more remote galaxies.
Hubble then plotted the distance to the galaxies against how redshifted they were, and he found that the data points fell along a neat line on the graph, so it looked like there was some kind of cosmic law at work. You don't get findings that are that consistent from a random process. It looked like there was a direct relationship between how far a galaxy was and how redshifted it was. If, and this was still an unsettled question, if the redshifts represented actual motion, then the farther away a galaxy was, the faster it was moving away from us. Bartusiak explains,
What Hubble saw was a definite pattern to the galaxy's retreat, a rule that was simple and yet so elegant. The velocity of the galaxies was found to steadily increase, rise in a linear fashion, as scientists say, as astronomers peered ever deeper into space. At double the distance, a galaxy's speed doubles as well. A galaxy 10 million light-years away travels twice as fast as a galaxy 5 million light-years distant. Hubble also calculated the rate of that increase. This number has since been amended, as better and better measurements were made over the years, but at first Hubble found that for every million parsecs outward, around 3 million light-years, the velocity of a galaxy increased by 500 kilometers per second. He referred to this factor as K, the same term introduced by others in earlier analyses. By the late 1930s, though, astronomers were regularly referring to it as H, Hubble's constant, later shortened to the Hubble constant.
When Hubble published his results, he became famous for this too. It was his second big discovery, and for many years, he got basically all of the credit for it. Even though Hubble was building on the work of Vesto Slipher, it was Hubble who got the attention. This was partially because of Hubble's own self-promotional efforts. For example, in 1930, the Dutch astronomer Willem de Sitter was writing an article in which he mentioned the distance-redshift relationship. De Sitter had previously proposed that relationship himself, but Hubble immediately sent him a letter reminding him that the work verifying this relationship had been done at the Mount Wilson Observatory, meaning by Hubble himself. Marcia Bartusiak writes,
Hubble conveniently forgot to tell de Sitter that most of the galaxy velocities he first drew upon in his 1929 paper were actually Slipher's data, which Hubble used without direct citation or acknowledgement, a serious breach of scientific protocol. Hubble partially made up for this nefarious deed by briefly referring in his next big paper on the redshift law, published in 1931, to the great pioneer work of V.M. Slipher at the Lowell Observatory. More gracious amends were made in 1953. That year, as Hubble was preparing a talk on the law of redshifts to be given in England, he wrote Slipher asking for some slides of his first 1912 spectrum of the radial velocity of the Andromeda Nebula, and in this letter at last gave the Lowell Observatory astronomer due credit for his initial breakthrough, albeit more than 2 decades late. I regard such first steps as by far the most important of all, wrote Hubble. Once the field is opened, others can follow. Privately, Slipher was bitter that he didn't get more immediate public credit, but was too humble and reserved to demand his share of the glory in 1929. He was at least honored by his peers for his contributions. The Royal Astronomical Society presented its highest award, the Gold Medal, to him in 1933.
Fortunately, the role of Vesto Slipher has come to be more recognized with time, and today he's given credit for the pioneering work he did in the field.
He said that there was still a question about how the redshifts of the galaxies were to be interpreted, and whether they really represented the galaxies moving away from us at a high speed. Why were people in doubt about this, and what else did they think might explain the redshifts?
The Doppler effect had only been discovered less than a century before, so it was still new, and people could imagine other possible explanations for why the redshifting might occur. Things other than the Doppler effect might be responsible for it. As a result, Edwin Hubble always hedged his bets. He would refer to the apparent velocities of the distant galaxies, but he didn't want to say that the apparent velocities were real, because if he committed himself to that explanation of the redshifts and it turned out to be wrong, his work would be tarnished. So he always referred to the fact of the redshifts, but left open the interpretation of why the redshifts existed. Marcia Bartusiak explains the perplexity at the time.
What did it all mean? What was causing the galaxies to flee from the Milky Way in such a methodical way? Were these swift velocities even genuine? It was easy to equate the redshifts with velocity, as that was the simplest interpretation and the most straightforward way to talk about the phenomenon in scientific papers. Everyone used the terms interchangeably. But perhaps some new law of physics was at work, and the galaxies weren't truly racing away after all. Maybe the retreat was entirely a chimera.
they had some reason to be suspicious. For example, they knew about one galaxy that appeared to be receding from us at 20% the speed of light, which is astonishingly fast. But the main problem was that it might be something other than the Doppler effect causing the redshifts. There might be some additional undiscovered law of nature causing them. When it came to what that was, or might be, there were a variety of proposals. For example, Willem de Sitter had some interesting ideas about the way space worked, and these might affect things. In a 1929 paper, Hubble discussed this possibility.
The outstanding feature, he wrote, is the possibility that the velocity-distance relation may represent the de Sitter effect, the most active model then in play. Maybe the light waves were lengthening as they traveled, setting up the illusion of movement. Or maybe matter was truly scattering outward due to the weird nature of de Sitter space.
And there were other proposals, as we'll hear later.
If it at least looked like the overwhelming majority of the nearby galaxies that we could measure were moving away from us, how did the idea emerge that this was something that applied to the whole universe and that the universe itself was expanding?
To understand that, we need to go back a bit in time and look at another line of research that was underway. In 1905, Albert Einstein had published 4 revolutionary papers. The papers were so revolutionary with such far-reaching implications, and they came out so fast that 1905 is referred to as Einstein's Annus Mirabilis, or Miracle Year. One of the papers introduced Einstein's theory of special relativity, and 10 years later, in 1915, he followed this up with a more general theory, known appropriately enough as the general theory of relativity. But general relativity was unproven at the time. One of the mysteries that had been bothering astronomers was that the planet Mercury didn't seem to be orbiting the sun the way Isaac Newton's law of gravitation predicted. We talked about that way back in episode 20 on the lost planet Vulcan, which was believed to be a planet closer to the sun than Mercury, and its gravitational influence was thought to be pulling Mercury away from where Newton's equation said it should be. As we discussed, some scientists thought that they had spotted the planet Vulcan, but later ones couldn't find it, and so the idea that there was an additional planet between the sun and Mercury fell out of favor, meaning that we didn't have a good explanation for why Mercury was moving the way it was. Until Einstein, because his new general theory of relativity did predict it moving in this way. So that was something. Still, confirmation for general relativity was needed, and another prediction of general relativity was that the sun is heavy enough to bend the light of distant stars as that light passes close by the sun. And that's the principle behind what is now known as gravitational lensing. Well, in 1919, the British astronomer Sir Arthur Eddington was able to view an eclipse of the sun, and his observations showed that the sun does indeed bend the light of distant stars. So general relativity was confirmed. Shortly after this, a Russian mathematician named Alexander Friedmann was exploring the mathematical implications of general relativity. Friedmann was not an astronomer, and he was approaching this from an entirely mathematical angle, but he wrote a couple of papers on the subject in 1922 and 1924, and he wasn't tying this to recent astronomical discoveries. It was just a thought exercise. But Marcia Bartusiak writes,
his sole goal was to try out possible solutions to Einstein's equations when applied to the entire cosmos. Like Einstein, he too filled his model universe with matter, but this time had it rapidly moving as the eons passed. Moreover, depending on the amount of matter, this movement of space-time could be an expansion, a contraction, or even an oscillation between the two states. We shall call this universe the periodic world, he wrote in his report. Friedmann even computed an age for the universe, a first in the annals of astronomy. He arrived at a figure of 10 billion years, not far from today's consensus of nearly 14 billion years, although Friedmann considered his estimate more a curiosity. He made sure to note the age could also be infinite. But all in all, his paper was predominantly an exercise in relativistic mathematics rather than cosmology, which is why it received so little attention at the time. Friedman made no mention of nebula, radiation, or redshifts, nor did he promote a cosmic expansion over a contraction. The journal, in fact, had indexed his article under relativity theory, making no reference that it dealt with cosmology, which is why it was easily overlooked.
One reason that Friedman's idea was overlooked is that the physicists and the astronomers at the time weren't talking to each other about the right subjects.
At this stage, most general relativists weren't terribly interested in astronomy, and astronomers who had more at stake in this quest didn't yet make the connection, believing that such models of the universe were more like mathematical toys, fun to fiddle with but hardly attached to the real world. They didn't take them seriously.
And unfortunately, Friedman didn't live much longer.
In 1925, he became ill with typhoid, just a month after conducting a record-breaking balloon ascent, an altitude of 4.6 miles, to make meteorological and medical observations. He soon died at the age of 37.
So Friedman didn't live to develop the theory. However, he had suggested that Einstein's equations were consistent with the idea of a universe that could be expanding, contracting, or alternately both. The breakout would thus come through another channel, a Belgian Jesuit priest named Father George Lemaitre. He had studied in England under Sir Arthur Eddington, and he traveled to the United States for further studies. He was interested in the right questions, linking the worlds of general relativity with astronomy.
He made sure to attend the 1925 Washington meeting of the American Astronomical Society, and was in the audience when Henry Norris Russell read Hubble's paper on the existence of other galaxies. While others in the room were focused on Hubble having ended the great debate, Lemaitre was 2 jumps ahead. Though new to astronomy, he quickly realized that Hubble's discovery could also be applied to fashioning models of the universe. The newfound galaxies could be used as markers to test the condition of the universe as predicted by general relativity. Later that year, while at MIT to complete an additional PhD, he began modifying de Sitter's cosmological model. Before returning to Belgium, he visited Slipher at the Lowell Observatory in Arizona and also journeyed to sunny California in order to meet Hubble and learn of the latest distance measurements of the Spiral Nebula.
As a result of these studies, he wrote a paper in 1927, but it didn't attract much notice.
Few had seen the article titled A Homogeneous Universe of Constant Mass and Increasing Radius Accounting for the Radial Velocities of Extragalactic Nebula. Because for some unknown reason, Lemaitre had published it in an obscure Belgian journal, Annales de la Société Scientifique de Bruxelles, Annals of the Brussels Scientific Society, rather than a publication on every astronomer's must-read list.
But in the paper, he proposed that based on Einstein's general relativity, the whole fabric of the universe could be expanding, carrying the galaxies with it. The paper finally came to notice in 1930 when his former professor, Arthur Eddington, was trying to resolve a debate of the day. People had been trying to work out the implications of Einstein's equations, and there were different models for how the universe might work. One was proposed by Willem de Sitter, and another was proposed by Einstein himself. At a meeting in 1930,
Arthur Eddington casually wondered aloud why only 2 cosmological models, Einstein's and de Sitter's, had so far come out of general relativity to describe the universe. Were other solutions possible, ready for plucking within Einstein's equations? A number of respected mathematicians had been sporadically tinkering with the models, offering up modifications, but none generated wide interest. Was that the end of the road? Einstein and de Sitter had each started with different simplifying assumptions and so arrived at different solutions. But they did have one thing in common. Both took for granted that the overall structure of space-time was static, fixed, and rigid. I suppose the trouble is that people look only for static solutions, noted Eddington at the meeting. It was easy to imagine a massive object like a star indenting space-time in a very local and specific location. But could the entire fabric of the cosmos across the span of the universe be changing as the eons passed? Could the universe itself be dynamic? It seemed more realistic and plausible to imagine the galaxies traveling through space rather than space-time itself varying, so everyone insisted on a cosmic space that did not move.
When Lemaitre read Eddington's published remarks, he wrote his former professor a letter and said, I did write a paper on that 3 years ago, at which point Eddington was immediately galvanized.
Looking back over the 1927 paper, he at last recognized its significance and with great enthusiasm made up for his blunder. He speedily sent de Sitter a copy of Lemaitre's article, writing at the top, "This seems a complete answer to the problem we were discussing." De Sitter as well grasped the brilliance of Lemaitre's approach, calling it ingenious and immediately abandoning his own solution. Eddington soon arranged for Lemaitre's paper to be translated and reprinted in the March 1931 issue of the Monthly Notices of the Royal Astronomical Society, where it could at last be given a proper showcase.
And the paper itself was revolutionary.
2 full years before Hubble provided the definitive observational proof of the galaxy's redshift, Lemaitre unveiled a cosmological model in which the radius of the universe increases and the galaxies surf outward on the wave. The receding galaxies, as Lemaitre described it in his paper, are a cosmical effect of the expansion of the universe. From our perspective, it appears that all the galaxies in the universe are rushing away from us, that we are somehow situated at the very center of the cosmic action. But in reality, you would observe the same dash outward from any other galaxy in the universe. Lemaitre was the first to say directly that the galaxies are fleeing from us because space-time at each and every point throughout the cosmos is continually stretching. The galaxies are not rushing through space, but instead are being carried along as space-time inflates without end. The embedded galaxies are simply going along for the ride.
However, not everyone liked this idea. Even though Eddington and de Sitter were now on board, Einstein was definitely not.
In October 1927, just 6 months after his paper came out in the Belgian journal, Lemaitre met with Einstein during the 5th Solvay Congress in Brussels, a triennial meeting of the world's top physicists, and the two had a brief chat about Lemaitre's breakthrough in the city's Leopold Park. It was at this time that Lemaitre first heard from Einstein about Friedmann's similar solution. By then, Einstein no longer had any objection to the mathematics in either man's model, but he was still repelled by the image of the cosmos that the models of both Friedmann and Lemaitre conveyed. "Your calculations are correct, but your physical insight is abominable," asserted Einstein, who could not and would not imagine a universe in motion.
In fact, Einstein disliked the idea of a dynamic universe so much that he included an extra term in his equations. He published his general relativity field equations in 1915, and it was realized that the role of gravity in these equations would result in a dynamic universe, one that either expanded or contracted. But Einstein believed in a static universe, so in 1917, he introduced a new term in the equations. The term was known as the cosmological constant, and its function in the equations was to counterbalance gravity and keep the universe from either expanding or contracting.
Did Father Lemaitre get credit at this time for the idea of an expanding universe?
Not at first. If you check out a lot of books and videos on astronomy, you will frequently hear that Edwin Hubble proposed the idea of the expanding universe, but he didn't. What he did do was document the redshift of galaxies, building on the work of Vesto Slipher. But Hubble himself was always cautious about the meaning of those redshifts. He pointedly did not claim that the universe was expanding, just that the galaxies were redshifted. As a result, Marcia Bartusiak writes,
Hubble did not really discover the expanding universe in 1929, as written up in textbooks and commonly presumed these days. The realization did not actually occur until Hubble's data could be viewed with Lemaitre's model firmly in mind. Lemaitre, far more than Friedman, had linked his model with ongoing astronomical observations. His solution was described as a brilliant discovery. Top mathematical theorists began to flock to the new field of relativistic cosmology, both to extend the model and to produce variations on Lemaitre's original theme of a universe in bloom.
So, once again, Hubble ended up getting credit for something that was largely another man's work. But also, fortunately, this situation has been redressed in recent times, and Father Lemaitre's work has been receiving more credit for pioneering this idea. The proposal got physicists and astronomers talking to each other in a new way because the redshifts of galaxies still had not been definitively explained, and they wanted to talk about this, which led to some interesting discussions at Edwin Hubble's house in California, where his wife Grace played hostess to the scientists. Marcia Bartusiak writes,
Astronomers and theorists previously resided in separate domains, but now he got them talking. Grace Hubble recalled the commotion it created in her household shortly after Lemaitre's model got wide circulation.
About every 2 weeks, some of the men from Mount Wilson and Caltech came to the house in the evening. Astronomers, physicists, mathematicians. They brought a blackboard from Caltech and put it up on the living room wall. In the dining room were sandwiches, beer, whiskey, and soda water. They strolled in and helped themselves. Sitting around the fire, smoking pipes, they talked over various approaches to problems, questioned, compared, and contrasted their points of view. Someone would write equations on the blackboard and talk for a bit, and a discussion would follow.
There was much to argue about. Those still skeptical of general relativity were offering other explanations for the outward march of the galaxies. British cosmologist E. Arthur Milne, for example, posited that the expansion of space-time was merely an illusion. Space was steady as a rock, but the spiral nebula, upon forming, started moving in random directions and with different velocities. Over the eons, the nebula with the fastest speeds naturally moved farther out, setting up the appearance of a cosmic expansion. It was a model that philosophically pleased Milne, who didn't believe space could possibly curve, bend, or move. Caltech astronomer Fritz Zwicky proposed that light waves, as they traveled through space, could be interacting with matter, setting up a sort of gravitational drag. The more a light wave traveled, the more it lost energy, shifting its wavelength toward the red end of the spectrum. This could explain why the nebulae furthest out displayed the largest redshifts. Space wasn't expanding at all. The photons of light were simply getting weaker and weaker in their journey through a matter-filled cosmos. Hence, this model came to be known as the tired photon or tired light theory. There was no natural way to explain how this would happen. It required a new law of physics, but that didn't deter Zwicky at all. He was a legend among astronomers for his chutzpah.
So there were competing explanations for the galactic redshifts, and that would result in a non-expanding universe. However, Lemaitre's theory got a big boost in 1931 when Albert Einstein made a trip to California.
Aware of Einstein's dislike for publicity, his California host tried to dispense with an official welcome as in New York, but to no avail. Upon docking in San Diego on New Year's Eve, the German visitors had to endure 4 hours of speeches, presentations, tours, and a radio talk. Only after all the hoopla had ceased were Einstein and Elsa finally taken northward by car, eventually settling into a small Pasadena bungalow specially renovated and furnished for their stay.
And a few days later, in Pasadena, near the Mount Wilson Observatory, Einstein did something startling.
Up to this point, he'd been very wary of considering a universe in restless motion, curtly dismissing the models fashioned by both Friedman and Lemaitre. Einstein by far preferred a universe that stayed put. But on that day, he at last conceded that the secret of the cosmos had undoubtedly been revealed by Hubble's observations. Einstein at last let go of his spherical universe. A gasp of astonishment swept through the library, according to an Associated Press reporter in attendance. At a follow-up session a week later, Einstein went further and announced that the redshift of distant nebulae has smashed my old construction like a hammer blow, swiftly swinging down his hand to illustrate the point to his audience. Einstein, at this stage, recognized that he no longer needed his cosmological constant to describe this dynamic universe. His original equations could handle the cosmic expansion just fine, which pleased him immensely. From the start, he had had qualms about the ad hoc addition, believing the constant tarnished the formal beauty of his theory. Tacking on the extra term, he reportedly said, was the biggest blunder he ever made in his life.
For many decades, it was regarded as Einstein's biggest blunder, and the cosmological constant was retired from the equations. But his blessing of the idea of a dynamic universe gave the idea more credibility, and this led to a natural question. If the universe is expanding, what does that say about how it began?
Lemaitre submitted a short note to the journal Nature with the splendiferous title, The Beginning of the World from the Point of View of Quantum Theory. If we go back in the course of time, wrote Lemaitre, we find all the energy of the universe packed in a few, or even in a unique, quantum. If this suggestion is correct, the beginning of the world happened a little before the beginning of space and time. I think that such a beginning of the world is far enough from the present order of nature to be not at all repugnant. We could conceive the beginning of the universe in the form of a unique atom, the atomic weight of which is the total mass of the universe. This highly unstable atom would divide in smaller and smaller atoms by a kind of super-radioactive process. He called his initial compact cauldron the primeval atom. Today's stars and galaxies, he surmised, were constructed from the fragments blasted outward from this original superatom.
This idea fit with what was being learned about radioactivity in the mid-20th century. The nuclei of atoms are made up of protons and neutrons, but protons have a positive electrical charge, which means that they repel each other. Like if you hold the north or south ends of two magnets together, they repel each other. That means that the electromagnetic force of the protons in the atomic nucleus is trying to force them apart and blow up the atom. The reason they don't blow up is because there's a stronger force known as the strong nuclear force that holds them together. Also, the neutrons in the nucleus have a neutral charge and they serve as a buffer so that the protons aren't so closely packed. But the strong nuclear force is only so strong and the neutrons can only do so much buffering. So if an atom gets really big, it gets unstable. That's why large elements like element 92 or uranium and element 94 or plutonium are radioactive, and we can make nuclear reactors and bombs out of them because the atoms are so big that the protons don't like being jammed together, and they get wobbly, unstable, and start spitting out nuclear particles, eventually turning into other more stable elements. So if all of the protons and neutrons in the universe were collected into one big atomic nucleus, with electrons buzzing around it like a giant primordial atom, you can imagine how radioactive it would be. It would be begging to explode. And that's what Father Lemaitre proposed as responsible for the beginning of the universe. Still, not everyone was convinced. One person who was definitely not convinced was the British astronomer Sir Fred Hoyle. He believed that the universe did not have a beginning, that it was eternal. As a result, he came up with an alternative model known as the steady-state theory. His goal was to explain why the galaxies were moving away from us and yet have the universe be eternal. The way he did this was by proposing a form of continuous creation that he said was happening in the universe. Yes, the galaxies were moving apart, but new matter was being created between the galaxies, which in time would lead to the development of new galaxies. So as the galaxies moved further apart, they wouldn't just vanish over the cosmic horizon, they'd always be replenished. Hoyle called the force creating this new matter the creation field or C field. And so his model involved a kind of continuous creation of matter. And you could have the universe expanding without it ever having a beginning. Well, Fred Hoyle was a rather gifted communicator, and he was asked by the BBC to give some lectures on science on the radio. On March 28, 1949, he was giving a lecture on the radio about the universe, and in it, he said this:
"The recession of the galaxies does not give the only observational test that a theory of the expanding universe must satisfy. During the past few years, astronomers have developed a number of further requirements. Although I don't wish to go into these in detail, I might mention that it is now possible to determine the age of our own galaxy and of several neighboring galaxies with a substantial degree of accuracy. The result is about 5 billion years. A satisfactory theory must provide for this age, neither more nor less. We now come to the question of applying the observational tests in earlier theories. These theories were based on the hypothesis that all the matter in the universe was created in one big bang at a particular time in the remote past."
And that was it. That's how the beginning of the universe got the name, the Big Bang. The term was coined by Fred Hoyle in the radio address, and he didn't even believe in the theory, because he went on to say,
"It now turns out that in some respect or other, all such theories are in conflict with the observational requirements, and to a degree that can hardly be ignored. Investigators of this problem are like a party of mountaineers attempting an unclimbed peak. Previously, it had seemed as if the main difficulty was to decide between a number of routes, all of which seemed promising lines of ascent. But now we find that each of these routes peters out in seemingly hopeless precipices. A new way must be found. The new way I am now going to discuss involves the hypothesis that matter is created continuously."
and he went on to describe his continuous creation theory that would result in the universe having a steady state rather than a beginning. But the tide was turning against him, and in the 1960s, it turned decisively against him because in 1964, something unexpected happened. There were two scientists working for Bell Labs, Arno Penzias and Robert Wilson. They weren't doing anything connected with cosmology or the Big Bang. Instead, they were working on a device known as the Holmdel Horn Antenna in New Jersey. The purpose of the antenna was to be used in satellite communications and in radio astronomy, which is a kind of astronomy that studies stars by looking at the radio waves they emit, since radio waves are just a kind of invisible light. They're not in the set of frequencies we can see with our eyes, so they're not visible light, but they are on the electromagnetic spectrum. But Penzias and Wilson were having a problem.
1963. 30-year-old Penzias and his 27-year-old colleague Robert Wilson began work on a new antenna in New Jersey. Initially, they were only studying cosmic radio waves, but they would stumble on one of the greatest discoveries of all time. As they started to test their equipment, they detected an unexpected background noise.
It was additional signal, and it appeared to be coming from the sky. We eliminated very carefully the ground, even the solar system, because we did this winter to summer, seasonal variation, man-made sources of equipment. All these things were eliminated.
In desperation, the two scientists began to wonder whether the strange signal might have another, more earthly origin. They found there were pigeons roosting in the antenna, and it was covered with droppings. They wondered if the pigeons were the source of the strange signal. There was only one solution. The droppings and the pigeons would have to go.
We finally got around to removing the pigeon droppings. We also had to remove the pigeons. That was a difficult problem because they turned out to want to come back, and we mailed them off to another site.
But even with the troublesome pigeons gone, the mysterious signal would not disappear.
And so we were left with the almost inescapable conclusion that this radiation was coming from the sky. I could not account for it.
The strange signal detected by Penzias and Wilson would turn out to be one of the most important scientific discoveries of all time.
To understand the importance of what Penzias and Wilson had discovered once they cleared away the pigeon poop, we need to talk for a moment about the science of the Big Bang. The original idea that Father Lemaitre had, that the universe may have had a start with a single atom that exploded, had been discarded. Our whole universe was in a hot, dense state, and then expansion started, but the energy density was way too high for there to be a single organized atom with a single nucleus of protons and neutrons and electrons orbiting it. In fact, the energy density was far too high for there to be protons and neutrons at all. We now know that protons and neutrons are made of smaller particles called quarks and gluons, and the energy density was so high that the formation of protons and neutrons had to wait until the expansion of the universe lowered the density to the point that gluons could start gluing quarks onto each other, producing protons and neutrons. So originally, there weren't protons and neutrons, there weren't atoms. After the protons and neutrons had formed, they still needed electrons to become atoms, and that took a while.
If there weren't atoms yet, what was the universe like once the protons and neutrons formed?
During this period, the spaces between the protons and neutrons were filled with a plasma of electrons, a kind of particle soup. And light could not travel very far as a result because particles of light, or photons, interact with electrons. It would be kind of like shining a flashlight in a thick cloud of smoke. The light wouldn't get very far before it would be absorbed. So for quite a while, the early universe was actually dark. In fact, it was dark for about 300,000 years. But then, 300,000 years after the Big Bang, when the universe was about the size of the Milky Way galaxy, the density became low enough that electrons could start attaching themselves to protons and forming atoms.
Is that how we got all the elements that exist today?
No, not all of them. The original atoms that formed were all very simple. They were almost all element 1, or hydrogen, which has 1 proton and 1 electron. Or some of them were element 2, or helium, which has 2 electrons, 2 protons, and 2 neutrons. A very few atoms were like element 3, or lithium. This initial formation of atoms in the wake of the Big Bang, or 300,000 years after the Big Bang, is known as Big Bang nucleosynthesis, and it's how we got the first batch of simple atoms. More complex atoms were formed later by stars, and that can happen in a number of different ways, which are known by names like stellar nucleosynthesis and supernova nucleosynthesis. But the original Big Bang nucleosynthesis basically gave us hydrogen and helium. In fact, the hydrogen atoms are so simple that when you drink a glass of water today, a lot of the H, or hydrogen, in the H2O that you're drinking are hydrogen atoms that were formed by the Big Bang nucleosynthesis. The same is true of the hydrogen atoms in the water in your body. Those atoms are that old, just under 13.8 billion years old. In any event, this atom-forming event, which is known as recombination, caused the electron plasma fog to dissipate. As the electrons got gobbled up and became attached to atomic nucleuses, the universe became clear, and light could suddenly travel. It was as if the light in the universe switched on, and the universe became a clear, bright place. That initial flood of unleashed light after the formation of the first atoms is still out there, traveling through space. And in the billions of years since then, it's shifted down as the universe has expanded to the microwave part of the spectrum. So now it's called the cosmic microwave background, because it's background radiation that fills the entire cosmos with microwaves.
The existence of the cosmic microwave background, or CMB, had been predicted as a consequence of the Big Bang, correct?
Yes, in fact, as early as 1948, some scientists had predicted that space should be filled with this radiation and that it would have a temperature of something like 5 degrees Kelvin, which is just 9 degrees Fahrenheit above absolute zero, the coldest it can get. Well, the radiation that Penzias and Wilson found was in line with this estimate. It was actually 2.7 degrees Kelvin, or about 4 degrees Fahrenheit above absolute zero. And when the dust settled and people had a chance to think about what Penzias and Wilson had found after they cleared away all the pigeon poop, they realized that the cosmic microwave background was the leftover radiation from the atom-forming recombination event. It's the light that was unleashed by the creation of the first atoms, which means it's an echo of the Big Bang. As a result of this discovery, the steady-state hypothesis steadily lost ground. Its advocates like Fred Hoyle continued to argue for their theory, but the astronomical community at large regarded Penzias and Wilson's discovery as the proof needed for the Big Bang. And so, 14 years later, in 1978,
we're here at Bell Laboratories, where I have Dr. Robert Wilson next to me and Dr. Arno Penzias, who have just been informed that they've received the 1978 Nobel Prize in Physics. What does one do when you first hear about winning a Nobel Prize?
Oh, I was very pleased about it. First thing I did was try to wake up, because I learned from a telephone call when I was still asleep. And then the next question is the authenticity of the news. It takes a while for it to soak in that it's all real.
I suppose there are pranksters in this world that might call you up and tell you you won the Nobel Prize. What about you, Arno?
And we know several of them.
Yeah.
There was one more major discovery yet to be made, though. In the 1990s, new discoveries started showing that the universe isn't just expanding, it's accelerating, flying apart faster and faster. In 1992, the COBE, or Cosmic Background Explorer satellite, measured the cosmic microwave background and provided evidence that the expansion of the universe was accelerating. This was a huge discovery because at the time, people were expecting the mass in the universe to gradually slow its expansion. Gravity pulls mass together, and so they thought that all the mass in the universe will eventually slow it down. And the question at the time was whether there was enough mass in the universe to merely slow the expansion, but letting it keep going forever, or whether there was enough mass to close the universe by causing the expansion to not just slow, but stop and then reverse itself and cause the universe to fall back inward in a big crunch. A lot of people don't like the idea of a universe with a definite beginning, and they were hoping for a big crunch scenario, which might allow another universe with a new Big Bang to follow ours. That would allow for an oscillating universe with no beginning and no end, just a series of big bangs followed by big crunches, or big bounces, as they're sometimes called.
Was it a shock when astronomers found out that the expansion of the universe is not slowing down, that it's actually speeding up?
Absolutely, and it meant our universe should fly apart forever with no big crunch. The evidence from the cosmic microwave background was then verified in 1998 in another way by a Nobel Prize-winning set of observations of distant supernovas. A team measured the distance to a set of supernovas and also looked at how redshifted they were, measuring the speed at which the galaxies are moving away from us, and they again found that the universe seems to be speeding up. But to make something accelerate, you need to apply energy to it. After all, that's Newton's first law of motion, that things will move at a constant velocity unless you apply a force to them. So if the universe is expanding faster and faster, that means some kind of force is being applied to it to make this happen. And since we can't otherwise detect this force, scientists named it dark energy, which is not the same thing as dark matter. We talked about both dark matter and dark energy in episode 83, The Case of the Missing Universe. But the key thing for our episode today is that the apparent discovery of dark energy, because not everyone is convinced it exists, casts new light on what Einstein thought was his biggest blunder. In light of dark energy, no pun intended, scientists realized that you could think of dark energy as a kind of cosmological constant, just like the one Einstein first introduced into his equations and then removed. Now it looks like there may be a cosmological constant after all, and it's what's stepping on the universe's accelerator and causing it to fly apart faster and faster. But that is the story of how we discovered the Big Bang. But we still need to talk about some theories.
Before we talk about those theories, we would like to take a moment to thank our patrons who make this show possible, including Colin H., Marna J., Heather T., Dan H., and John P. Their generous donations at sqpn.com/give make it possible for us to continue Jimmy Akin's Mysterious World and all the shows at StarQuest, and you can join them by visiting sqpn.com/give. Jimmy Akin's Mysterious World is also brought to you by Fearvento Law PLLC, now assisting clients with expungements and set-asides of Michigan convictions. To learn more, call 231-202-3321 or go to fearventolaw.com, FIORVENTO law.com. And by delivercontacts.com, offering contact lenses at low prices with free delivery. Visit delivercontacts.com. Jimmy, what theories are there about the Big Bang?
There are a lot of theories about the Big Bang, a lot of different versions of it and how it's supposed to work. In fact, there are many more than we can discuss today. So we'll have another future episode dealing with the science of the Big Bang and all of the ideas about it, both from the faith and the reason perspectives. However, today we'll close by just noting a couple of things. From the faith perspective, we'll briefly talk about what the faith has to say about the Big Bang, and from the reason perspective, we'll discuss whether it was technically a bang or explosion.
Then let's look at the faith perspective. What does the Catholic Church have to say about the Big Bang?
The Big Bang is a matter of science rather than faith, so the Church doesn't have a teaching on it. The Big Bang must stand or fall based on the scientific evidence and arguments. However, the Church does not have a problem with the idea of the Big Bang. According to the Catechism of the Catholic Church,
the question about the origins of the world and of man has been the object of many scientific studies, which have splendidly enriched our knowledge of the age and dimensions of the cosmos, the development of life forms, and the appearance of man. These discoveries invite us to an even greater admiration for the greatness of the Creator, prompting us to give him thanks for all his works and for the understanding and wisdom he gives to scholars and researchers.
So the Catechism states that modern scientific studies, by which they mean the ones we've been talking about in this episode, have splendidly enriched our knowledge of the age and dimensions of the cosmos. While that doesn't teach that the universe is billions of years old, it is supportive of the idea. The Church does not take a young Earth creationism view of things, and we've talked about that on the program before. You can go back and listen to episode number 119, episode number 120, and episode number 121 if you'd like to learn more about that, because we discussed the issue in depth. Also, Blessed Pope Pius XII was himself a big supporter of the Big Bang. In fact, Father Lemaître warned him not to overstress the implications of the Big Bang for proving the existence of God. We'll have a link to a speech that Pope Pius XII gave in 1951 where he talks about the state of the evidence at the time, and he strongly supports the Big Bang. Finally, before we leave the faith perspective, I want to issue one caution. Do not identify the Big Bang with the moment in Genesis where God says, "Let there be light." The creation of light in the Bible is not the same thing as the Big Bang in cosmology. I mean, remember, just for one reason, I won't even go into the biblical reason, but for one scientific reason, the Big Bang did not immediately result in light shining. That came 300,000 years later. But we will talk more about that in our future episode on the science and faith of the Big Bang. But until then, we'll also have a link to an article I wrote that discusses the subject.
Now, what do we need to say about the Big Bang from the reason perspective today?
I just want to clarify the idea that just as the biblical creation of light is not to be identified with the Big Bang, I also wanted to clarify a common scientific misunderstanding. Fred Hoyle's name, the Big Bang, as catchy as it is actually somewhat misleading. The universe did not literally go bang. It wasn't an explosion. When an explosion goes off, like if you set off a firecracker, it throws material out through space, which is standing still. The firecracker is in one location in space, and it throws out material to other locations in space. That is not what is happening with the beginning of the universe. As we discussed earlier, it isn't that the galaxies are moving through static, unmoving space. Instead, it's space itself that is expanding, and the galaxies are just being carried along for the ride. Rather than thinking of a firecracker, think of a balloon. If you put stickers on the surface of the balloon representing galaxies, and you then blow up the balloon, you inflate it, the skin of the balloon expands, and the galaxy stickers move further away from each other as that happens. That is much more like the beginning of our universe. Rather than the Big Bang starting at a point in space, all of space, all of the currently visible universe, was originally compressed, and that space then started expanding like a balloon. So the Big Bang did not happen at the center of the universe. For all we know, there isn't a center to the universe. Instead, the Big Bang happened everywhere all at once, and it's still happening as the universe keeps expanding.
Jimmy, what is your bottom line on the Big Bang in the beginning of the universe?
The Big Bang is the proposal that the universe began in a hot, dense state and then began expanding. This proposal is scientifically well supported. The redshifts of galaxies point to the universe being much smaller in the beginning. The cosmic microwave background points to the moment when the first atoms formed and the light in the universe was unleashed. And the most recent evidence indicates that the expansion of the universe is accelerating, so it will not collapse back in on itself. And the story of how we found the Big Bang is a fascinating tale that represents a major achievement of the scientific enterprise.
Jimmy, what further resources can we offer on this topic?
We'll have a link to Marcia Bartusiak's excellent book, The Day We Found the Universe, also information about spectroscopy, an animation of the Doppler effect, also the car horn demonstration of the Doppler effect that we heard, info on Fred Hoyle's steady state model, a video about Penzias and Wilson's discovery, also an interview with them on winning the Nobel Prize, as well as my article on the Big Bang and apologetics, Blessed Pius XII's speech on creation and the Big Bang, an article discussing Father Lemaître and his interactions with Pius XII, and also a statement by Saint John Paul II on science, faith, and the Big Bang.
So that does it for us for this time. We would love to hear what your theories are about how we found the Big Bang. You can let us know by visiting sqpn.com or the Jimmy Akin's Mysterious World Facebook page, sending an email to mysterious@sqpn.com, sending a tweet to @MYS_world, visiting the StarQuest Discord community at sqpn.com/discord, or calling our mysterious feedback line at 619-738-4515. That's 619-738-4515. 4515.
And I want to say a special word of thanks to Oasis Studio 7 for the video and animation work on this episode. They do really great work, and you can check it out at youtube.com/Jimmy Akin, which is my YouTube channel. If you have a need for video and animation work to be done, be sure to contact Oasis Studio 7. And while you're at my channel, I am trying to grow it. We're working on getting up to 40,000 subscribers. So I would really appreciate it if you would click the subscribe button and hit the bell notification so that you always get a video notification, whether it's Mysterious World or one of the other videos that I release.
Excellent. And also thank you to Melanie for providing a bit of voice work in this episode. Really appreciate that.
Yeah.
So Jimmy, what's our next episode going to be about?
Next week, we're journeying back to the world of the paranormal again for a two-part look at the practice of dowsing. We're going to be joined by Dr. Paul Smith, who was one of the original government psychic spies as part of the Defense Department's Stargate remote viewing program. But the Stargate program didn't just use remote viewing. They also used dowsing to find targets for the government. Paul is a dowser, and next week he'll be telling us about his own experiences with dowsing, as well as the different kinds of dowsing that exist. The following week, we'll be looking at dowsing from the faith and reason perspectives, and prepare yourself for a surprise. I was very surprised when I started researching the faith perspective and discovered what the Catholic Church has actually said about dowsing.
Very interesting. I'm looking forward to that. Folks, be sure to get your very own Mysterious World t-shirt or mug or more in our merchandise shop at sqpn.com/merch. You can find links to Jimmy's resources from our discussion on our show notes at mysterious.fm/245. And remember, to help us continue to produce the podcast, please visit sqpn.com/give. Jimmy Akin's Mysterious World is also brought to you in part through the generous support of our sponsors, including Aaron Ferguson Electric and Automation at aaronv.com, AARONV.com, making connections for life for your automation and smart home needs in North and Central Florida. Jimmy Akin's Mysterious World is also brought to you in part by Catechism Class, a dynamic weekly podcast journey through the Catechism of the Catholic Church by Greg and Jennifer Willits. It's the best book club, coffee talk, and faith study group all rolled into one. Find it in any podcast directory. Until next time, Jimmy Akin, thank you for exploring with us our mysterious world.
Thanks, Dom.
Once again, I'm Dom Bettinelli. Thank you for listening to Jimmy Akin's Mysterious World on StarQuest.